Next thing we are going to talk about is Newton's laws of motion. Now, you probably already have in your mind what Newton's 3 laws of motion are, but I almost 100% guarantee that what you have in your head are versions of the 3 laws or simplifications, and those simplifications are wrong. So if you state Newton's 3rd law as every action has an equal and opposite reaction, which has become the trope that is Newton's 3rd law, then in the exam that would be wrong, and it also isn't specific enough and it can lead to misconceptions. So what I'm going to do is I'm just going to pretty much give you Newton's 3 laws in this video, and that's basically all I'm going to do. What you need to do is make sure that you get them firmly into your head, because not understanding these is going to mean that you're going to struggle with pretty much any describe or explain style questions that could come up in the exam. So I know I've referred to Newton's laws before and I've given you definitions that match them, but these are the definitive ones. These are the ones that are on the right hand side of the page in red that I want you to make sure that you go away and learn. So, Newton's first law of motion. An object will remain at rest or keep travelling at constant velocity unless it is acted on by an external force. Easy peasy, we've already done that one, stays the same. So, an object's motion will only change if a force is applied to it. So, we should be absolutely fine with that one still. Newton's second law. So, Newton's second law is going to change now. It's going to be a little different. It's going to say the net force acting on an object is directly proportional to the rate of change of the linear momentum of that object. And the force and the change of momentum are in the same direction. So there's quite a big mouthful there. So the main bit is this bit here, but we just need to remember that the force and the change of momentum are in the same direction. So we need to know what momentum is then, don't we? Momentum is basically just mass times velocity for a moving object. Simple as that. We also talked about linear momentum, so we need to know about linear momentum, and particularly the conservation of linear momentum. So the principle of conservation of linear momentum says that for a closed system, in any specified direction, the total momentum of the objects before a collision is equal to the total momentum of objects after they have collided. So basically this is just another conservation law. Just like with energy, we've still got that caveat about it being a closed system, but we say that for a closed system, in any one direction, this momentum is going to be conserved even if we have collisions of objects. Okay? I'm going to look at that in a lot more detail, but don't worry, I just want to get these ideas in your heads and see if you can just get these terms learnt. Next up, we've got Newton's third law of motion, and what this says is that when two bodies interact, the forces they exert on each other are equal and opposite. Now, it's really, really important that you have this idea of there being two bodies and that the forces are being exerted by one upon the other. This is sort of the condensed version. The much longer version, we talk about body A acts upon body B, and then body B acts upon body A with an equal force that's equal in magnitude and opposite in direction. This is the simpler version, but you must have this idea of there being two bodies that are interacting. Now, we often talk about Newton's third law force pairs, so pairs of Newton's third law forces. And those forces have to act on different bodies. They must be equal in magnitude, they must be opposite in direction, and they must be of the same type. So you could get asked, is this pair of forces a Newton's third law pair? And if you can say no to any of those four things, you can very quickly rule out that they are a Newton's third law pair. So we just need to know these features of Newton's third law's paired forces. But again, remember the thing about there being two bodies and they act on each other. This is where it comes back into it here, that they must act on different bodies. So just to give you a nice summary where it's all on one slide, where it's nice and easy to see and follow, Newton's first law of motion states that an object will remain at rest or keep travelling at constant velocity unless it is acted on by an external force. Newton's second law of motion states that the net force acting on an object is equal to the rate of change of its momentum, and the force and the change of momentum are in the same direction. Newton's third law of motion states that when two bodies interact, the forces they exert on each other are equal and opposite. And we have the net force acting on a body is equal to the rate of change of its momentum, which we can get from Newton's second law. So just as a note how we would write that using algebra, net force equals rate of change of momentum, so F equals delta P over delta T. So that's another way that you can write that. The equation F equals ma, which we have talked about before, is a special case of Newton's second law of motion, and it's only true when mass remains constant. Because hopefully those of you who are sharp-eyed can remember that momentum was mass times velocity, so I have mass times velocity over time. Velocity over time is acceleration, so that's absolutely fine to be F equals ma as long as the m stays constant. We're going to get to slightly more complicated situations where that is not always true, which is why we needed the better version of Newton's second law. Okay, and that is it. We will practice these a lot, but make sure you learn them. The specifics and the details of this do matter. It's not good enough to just be sort of getting the idea with these. You've got to have them firm in your head. Okay, and that's it. If you've got any problems or queries, ask me when you see me in class.